Okay. If you just come, you can scan the QR code, and yeah, please scan the QR code. I'll be giving you a couple of minutes. And if you have any idea or thoughts or suggestion on how we can proceed the exam. So probably the quiz will be online quiz, but the final exam, my uh, my default will be on uh, offline for the final exam. But it depends on the situations. It depends on the situations. On also for students, if you are still having, uh, or if you have confirmed test confirmed positive at the dates of the final exam, then you might take the online test. Okay, so okay, I will stop this sharing and let me share the notes. Okay, so last time I mentioned that we will have a quiz, right? Next week. So the quiz will be online quiz. Well, it's not necessarily quiz, it's like a homework. So I will make like a homework, but it will have a percentage to help the quiz, all the total score for the quiz. Okay. So I will prepare online. You just need to click. So it's supposed to be like a homework. It's supposed to be like a homework for chapter 5. Will be include all chapter 5 from the beginning, definite integral, fundamental theorem of calculus, substitutions rule. They will be included in chapter 5. And I will announce in Moodle, so please check Moodle. So you can check the Moodle from I think next Tuesday. I will post after our class on Tuesday. So I will post regarding this online quizzes. Okay, so for today's lecture, we'll go through chapter 6. Okay, so chapter 6 is about the integral applications. Integral applications. So let me start with chapter 6. Integral applications. Okay.
Professor, I want to add
Yes.
something. During the quiz, do we have to join the Google Meet the same as today, or just
For the
yeah
quiz,
yeah?
no. I consider that like quiz homework. So you can click uh, whenever you have free time. But,
Oh,
but but
okay,
I will set maybe 4 to 5 days, okay, for the quiz. So it's
okay,
like practicing, exercising, but it's like a game. Like last time you have joined, I think. Um, we have a certain amount of time for each question. So it's like some games. Okay, so you can just join. Okay. So the
that's it.
percentage will be not as big as offline test. So it is smaller, but I think it will also can help your quiz in total. Okay. So I consider that as a mini quiz, like a mini quiz. Okay. So I prepare chapter 5 and then later chapter 6 and chapter 7. We will have each chapters as in a quiz. So every time we finish the chapter, maybe the week after, we'll post in the Moodle, and you need to click the link, and between the times you can choose. Okay, maybe I will, for example, if I put the link on Tuesday, probably you will have at least around 5 days to choose, okay? Or maybe from Wednesday to Sunday or Wednesday to Monday. Okay, depends. Okay, you can check the Moodle system later. Okay, okay, that's for the online quiz. Now let's move on to chapter 6. So the chapter 6 is it's supposed to be the integral applications. The integral application means that if we know that the integral is, we can represent the integral as an area under the function, right? So if we have this function of x, and if you want to, let's say, evaluate from a to b, and we are going to get the total area, okay? We can do that through the integrations, right? Through integrations of the functions, right? From a to b. Now, the idea in chapter 6 is start with, let me start with this. We have two functions. So we have f of x and we have g of x, okay? And both curves we are going to evaluate through the same endpoints. So from A to B, right? Now, the question is, what will be the area for this case, the S? Now, as we mentioned, that if we have, if we break down the area in between this curve, this is called the area between curves. Okay, if you want to make notes in your writing, this is called area between curves, the sections. So we are dealing with two curves, and we want to know the area between those two curves. Okay, okay. If we broke down this area, I'm making a small rectangle. Maybe. Okay. Now if we make this and let this become a delta x, and of course this will be our f of x, right? You can have f, let's say f at x, so some x, okay? And the other part will be g, right? Or in our case, this will be a negative g because it's in the bottom of the x-axis, right? So the length, the total length from here to the bottom here, this will be f minus g, right? And if we make the slicing with all rectangles, then we have these approximations. And as we mentioned in the integral, in the introduction of integral, we have the Riemann sum that is, and in this case, this will be the difference between f and g, right? Okay, this is approximating the rectangle. And as and getting larger, right? We are then define the limit as n going to be infinity of our sum or put it here. This will be equal to integral from a to b f of x minus oh, okay, f of x minus g of x dx. Okay, is the first uh, definition. And the idea behind this this integration is if y, let me write, if y f of x, or maybe let me write area bounded by y equal f of x, y equal g of x, and lines x equal a, x equal b, where f and g, they both continuous, and f of x is greater than g of x for all x in between a and b, and we can let area be an integration from a to b f of x minus g of dx. Okay. In a more illustrations, if you see this figure, I hope you can see clearly that this figure here, basically, if we imagine, first, maybe we can see this f of x. Okay, we know that the area is this, right? And then the second one, we know that the area for g will be here, right? So basically, the area between is the total area minus the area below, which is certainly this, and this is actually equal to this. Okay, this is one way to illustrate the visuals, okay, to understand what is going on in this area between the curves. Okay, let me give you a more practical example. Okay, I hope you can take notes, at least take notes for the Riemann and the integrations. And I think all the visuals here are understandable and not too complex. Okay, let me go through the other part. So let me give you example. Find area of region enclosed by parabolas y equal x squared and y equal to x minus x squared. So we are not given the other information aside from these two parabolas. So it's supposed to be the parabolas. This is just a usual parabolas. The second one is the negative parabola, which means we have this. So of course, if we combine those two, at least we will get into somewhere, right? We will get into some point that is intersecting, right? Now we can start imagine that we have some intersections for these two parabolas. We can start with this. And we can say that we can have some intersection at x0 and at x equal 1. Now, if you would like, we can also draw the parabolas to see that this will be the function at the top and x squared will be the function at below. Okay, so first you need to be sure that which one is the function that you are going to put on the top. Okay, and as we mentioned here that we have 0, 0, and 1, 1 for the point of intersection. Now we will have integrations from 0 to 1. Okay, according to what we have here, we will have 2x minus x squared and then minus x squared f minus g, right? And then dx. So we can factorize 2 outside. So we will have x minus x squared dx. Okay? And then we will have 2. And we can solve this, each one of them. And then plug in 1 and 0. So first is half minus 1 over 3 is 1 over 6. So it's 1 over 3. So the area between the curves is 1 over 3. So it's really helpful for us to sketch the graph, these two parabolas. Okay. Another note that might happen in this area between curves is we may have some notes. So we may have area between curves, between curves f of x and g of x. For some x, f of x is greater than g of x. For other x, g of x is greater than f of x. Then we can split. Split the interval. But we can write in more general. We can write with using the absolute value f of x minus g of x. But we need to define this absolute according to the interval. For example, we will write f of x minus g of x when f of x is greater than g of x, and g of x minus f of x when g of x greater of f of x. If you set up into a picture, then probably this will be what I mean. So we can separate the interval. For example, we can set up maybe another new interval here, which is the C or D, C, D. So AC will be S1, and D to B will be S3, and S2 will be C and D. But we still can write down into one single formula using the absolute value. So this absolute value means that in some part of the interval, f will be greater than g, but in some other part, probably g will be greater than f. I think one example to show how this happens is through the trigonometry. So some trigonometry will have this kind of um, sinusoidal. It has some amplitude, right? So perhaps some part will be negative, some part will be positive.
Professor, I want to
Yes,
ask,
yes,
in this case, if we, let's say we do an integral, we just do it normal, right?
yes. Do it normal. Do it normally. So the notions here is if you have, like, for example, this case, then you need to split this f of x minus g of x, for example, from a to c, and then plus from c to d. This is g of x minus f of x. Okay, and then plus from d to b. This will be f of x minus g of x dx. Okay. Yeah, something like that. So whenever this terms happens, this absolute value happens, which means that you need to consider the interval of integrations, which part that probably f will be higher and some other part g will be higher. Okay.
Okay, thank you, Prof.
Okay. Now, for example, if we look at uh, area bounded by curves y equals sine x, y equals cosine x, and then x equals 0, the line, and x equals pi over 2. So perhaps we can draw. Okay, if we want to draw, we can draw and imagine how the sine and cosine will collide or will be intersecting. Maybe we'll put around here. Okay. Now if we start with the cosine, so let's say this is the maximum of cosine, and this will be the pi over 2. So probably this will be the cosine. And sine will be start from the 0, and let's say at pi over 2 it's maximum, so it should be going through here. Well, it's not really proportional, but let's say that this is proportional. The point in the middle, if it is proportional, it should be pi over 4, right? Or if you want to make sure that this is pi over 4, we can say that sine x should be equal with cos x. So sine x over cosine x should be equal 1. So tangent x equal 1. In the first quadrant, x will be pi over 4, right? In our case here. Because we are only having conditions from 0 to pi over 2. So our area will be this A1 and A2. So this will be the cosine. This will be sine x. Now if you write in general, then the area we can write first from 0 to pi over 2. We can write, maybe we can write with terms this absolute cos x minus sine x and then the x, which means that this will have we can split with the middle point of pi over 4, that this will be cos x minus sine x, and plus from pi over 4 to pi over 2 sine x minus cos x. Okay, and then integrate plus cos x from 0 to pi over 4, and then plus this will be minus cos x and minus sine x from pi over 4 to pi over 2. So sine will be square root of 2 plus square root of 2, and then minus 1, and plus 0, minus 1, minus or plus square root of 2, square root of 2 over 2, and we have this is square root of 2, 2 square root of 2, minus 1, so it's minus 2. Okay, but of course, it seems takes time when you have this interval, right? However, remember that in integral in chapter 5, we have we get help from the symmetry, right? With symmetry. So if we can imagine that cosine and sine, they are actually complement each other, right? So if we have this part here, it should have their symmetry, right? Okay. What I mean is A1 is actually equal to A2, right? By symmetrical. So basically what I want to say is you can say that the area is twice of A1, which means that 2 if we want to calculate from 0 to pi over 4, we will have cos x minus sin x dx. And if we calculate from here, we see that this will be equal to 2 square root of 2 minus 1, and this is practically the same. Okay? So in area, if you can find the symmetry, my suggestion is use that symmetry because your calculation will be much simpler and you can easily integrate within the interval. Okay. Okay. Any questions from here?
Professor,
Yes.
how do the negative one come from?
Negative one, which the left one?
No, the right one.
This one?
Yeah. Negative one.
Negative one is from. So first, we input the pi over 4, right? This become this, right?
Yes.
And then minus, we input 0.
Oh, understand.
Yeah. From there. Okay.
Yeah, thank you.
Okay. Okay. The other um, the other part in this area between curves is if we have, for example, okay, let me give you a true example, and then we can have much more practical and clear way how we can solve most of the problems in this chapter. So let's say we start with find area closed by line y equal x minus 1 and y squared equal to x plus 6. Okay. Now let me give you the picture to help our investigations. But this is the uh, the the curve. Okay. So we may exchange this into x half y squared minus 3, and this will be x y plus 1. Okay. So why we need to change rather than x, we are using y. If we are going to, maybe we don't look at this first. Okay. So maybe we start with looking at this area between these two curves. If we let our assumptions based on dx, okay, which means that we are having rectangles here. If we imagine this rectangle and see through all the line here, see through all the curves here, there will be a slight problem here. what is this area? This is its own curve, right? Its own curve. Can we make it, like for example, if we have just this, and then this is the curve, and then this is another curve, I think this way we can have our area here. But how about here? Okay, now this is a problem, right? Now, instead of having the rectangle for the dx, we are using the rectangle for dy. So then that's why we have, rather than the top and bottom, we have left and right. Okay. So this is the rectangle. So if you feel confused on how we are connecting the first part to the second part, the previous one to this one, so imagine this being rotated. So for example, if we rotate this, it's actually same problem, right? The top minus bottom. Okay. So if you obviously can see before I rotate, then it's good for you. But if not, then the best way to look at is maybe you can rotate and you can see that the functions on the top minus the function on the bottom. That's always the case for area between curves. Okay. So let me put back to the original positions. So it means that we are going to have area. We are going to have um, xr minus xl. And of course, we need to find the intersection point, in which it's mentioned that it's 5, 4, and -1, -2. But we need to know for sure how do we make these numbers. So we have the x, and we need to take equal both sides. So y plus 1 equal half y squared minus 3. So we'll have half y squared minus y minus 4 equals 0. And then we may take this multiple by 2, and we get that this will be equal, this is 4, this plus 2. So y equal 4 and y equal -2. So from our equations, we get x, y plus 1 is 5, x plus 1 is -1. Okay, and that's how we get the point. We get the point, and this is how it looks like in the graph. And now we can set up our integrals. Okay. So in the chapter 6, the procedure or how the steps will be is usually we start by looking at the graphs. If we can draw the graph, that's better. We draw the graph, look at the graph, set the interval, or if the interval is on the intersection, then we need to find the intersection. And after that, we set up the formulation for the integration for the area. So we set up the area by taking this from -2 to 4. Okay. Now we are looking at the rectangle of dy. So we will have y plus 1, okay, y plus 1 minus half y squared minus 3 and dy. Okay, I think we can solve this. So we can set up the integral 1/6 y cubed plus y squared plus 4y from -2 to 4. So it will be negative 1 over 664 plus 16 over 2, 8 plus 16. That's the first one. Minus, this is minus 2, 8, 8 over 6, 4 over 3. Negative 2, 4, 2, minus 8. Then this will be equal to 24. 4 over 3. This will be 32 over 3 minus 4 over 3. Minus, it'd be negative 36 over 3. Negative 12, so negative 12. Minus 6. Minus 18. 24. Should be on 18. Okay. To give you more clear idea, maybe I'll give you this. Let me crop this here. Okay. Just to give you an idea on that the area in general is integral from C to D xr minus xl and dy. But some cases you can do both way. You can do dx, you can do dy. Depends on the functions. So I believe it's up to you to decide which method you are going to use. But some cases only works for dy, some cases only work for dx. So you need to be wise to look at the question. Okay. Let me check the okay. Okay, let me move to the next page. Okay. But so far, so good for the chapter 6. At least the idea behind the area between curves. Okay. Yeah, for area, I think that's really complicated. But if we move forward to the volume, I think that will be a little bit complicated, but not as much complicated for if you compare to calculus 2. That is pretty much all the integrals will be very complex because we deal not only single variable but multi-variable. Okay, but regardless, let's go to another example that I want to show you how we can solve this. The area between curves with dx or dy. So you can choose which one is your preference. Find area between curves y equal 1 over x. Y equal 1 over 4x, and then y equal x. Okay, so 1 over x, this is it's like an exponent, but it's reciprocal. This is just line, 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 right? So first thing, we need to draw. Okay, we need to draw and see how the graph looks like. So first, maybe draw the x, y equal x, that. Maybe, okay, maybe around this point. Okay, maybe the other is, so this is half, maybe this is 1 over 4. So let's say this is 1 over 4. Okay, let me make the 1 over x around here. Okay, let's make around that point. This is y equal 1 over x. So you can see that there are almost triangle area. Okay, so look-alike triangle in between these three curves, right? That is our area that we want to find. So perhaps we can start with finding the intersections, this intersection and this intersections, right? So first we can find intersection. Let me write intersection. So first finding intersection for 1 over x is equal x. Or we can say that we will have x squared equal 1. So x will be plus minus 1. Or in this case, we are having precisely x is 1, 1 here. Okay. Now the other will be 1 over 4x equal 1 over x. So this will be equal to x squared equal 4, or x will be plus minus 2, but in our case here, this will be 2. So when x is 2, then y will be 1 over 2. So when x is 2, y will be 1 over 2. That is our intersection. So we have these 2 points for the intersection. Now first, we can start with, if we define this like this one, we can say that this will be a1, or maybe let me make copy of this graph so that I won't draw again. So let's make copy, paste around here. Okay, good. Okay, let's say we have a1 and a2. Now you can see clearly from this point, this x equal 1, we can see that a1 is x minus 1 over 4x for the graph, for the area. So we can start the area is A1 plus A2. Okay. Let me move. Maybe move around here. So A1 start with integrations from 0 to 1 of x minus 1 over 4x dx. Or we can simply write x minus 1 over 4 as 3 over 4 x, right? I think no need this. Dx, okay. And then plus the a2 will be start from 1 to 2. That is the 1 over x minus 1 over 4 and an x. Okay, yeah. Now we can start with this plus 1 over x. This will be the ln, okay? Ln x, and then minus x squared over 8. This is from 1 to 2. The first one is 3 over 8. And then we put 2 ln 2 minus 4 over 8, and then minus ln 1 minus 1 over 8. So we will have, this is 0, negative 4 over 8 plus 1 over 8, it's negative 3 over 8. We'll cancel this too. So we will have, in total, just ln 2. Okay, clear, right? Okay, so this is the first method. If we observe another way, let me write it from here. Okay, another way we can take a look on this area. So we will have A1, A2. Okay, and of course, if you see A1, A2 in perspective of y, then we are going to have all terms will be in terms of variable y. Okay, so be x is 4y. Okay, and I think the rest will be the same. Okay, now the area is A1 plus A2. And now we are going to have, this is 0, this is half, this is 1, right? So we can start from 0 to half. Four y minus y, or 3y dy, right? And then plus the area 2, that will be 1 over y, from half to 1. This will be 1 over y minus y, and then dy. Maybe I will put the calculation on the sides, maybe here, and put this around a little bit left. Okay. Now 3y, we will have 3 over 2 y squared from 0 to 1 over 2, and then plus we have ln y, and then minus y squared over 2 from half to 1. Okay, now we are having, this is 3 over 8 plus ln 1 minus 1 over 2, that's the first one, minus ln half minus 1 over 2 squared will be 1 over 4, 1 over 8. Okay, 1 over 8. 1 over 2, we can write 1 over 2 as 4 over 8. So minus 4 over 8 plus 1 over 8. This will be equal to minus 3 over 8, in which we can cancel this, right? We can cancel. So we will have ln 1 is 0. So minus ln 2, minus ln half. Ln half is minus ln 1 minus ln 2. Or we can write this as the same ln 2. Okay, so this is the second way using the dy. So basically, for questions in asking the area between curve, it's up to you which one you are going to pursue. Okay, but some questions they have their own restrictions. For example, previous questions that asking these questions, this one, this one. This is difficult if you want to find true dx. Okay, the easier with UI. Before these questions, you can choose whatever path you are pursuing. You can choose dx or dy. Okay, perhaps we can start with some example, some other example. Check the questions. Let me go through. Okay, that's the number 2. Okay. Okay. Okay, let me move to next page. Okay, now questions, example. Find the area between the given curves. Between the given curves. maybe have 2 or 3 examples, and then if you still have time, we can move to next sections about the volumes. So this will be, so for number A, the curves is square root of x minus 1, and then x minus 1 y equal 1, and then B, y equal x cubed, and y equal x, and then C, y equal cos x, y equal 2 minus cos x from 0 to 2 pi. Okay, 3 questions. You can try. Okay, let me give you maybe 3 to 5 minutes, and then see if you can have some answer, at least for the first one, the second one, the first one. I think the first one. I give you a, Okay. Anyone got the answer? For the first one? Anyone calculate? Negative. Okay, Kim, negative 1 over 6. I think it should be not negative. It's 1 over 6, but it should be not negative. But I think you should have some mistake on the sign. But the numbers are correct. Okay, so if we try to look at the graphs, okay, first let me make a space between the questions. So first questions. So perhaps we start with the so we start with maybe this line. So we can write line as um, x equal or maybe y equal x minus 1, and this line is actually here, right? Or maybe a little bigger, maybe once. So this will be the line. So this will be y equal x minus 1. And then the square root x minus 1 at x equal 1, y 0 should be here and should be having that 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 line, okay, curve. So this will be y equals square root of x minus 1. So the area, first, if you want to try using the dx, we can use that. We can take dx as this rectangle, right? Dx. So we can start to write on the area as from or maybe finding the other intersection as well. So maybe finding the intersections. Let's equaling these two. So we will have x minus 1 and then x squared minus 2x plus 1. We squared both of them. We take squared, we take squared. So we will have x squared minus 3x plus 2. So x minus 1, x minus 2. So x equal 1, x equal 2. So this will be x equal 2. Okay, now what's next is integrations from 1 to 2. Square root of x minus 1 minus x minus 1. So if you are maybe having difficulty from this part, perhaps you can start looking at another alternative. We can solve this, and this should be, maybe I will solve this first. Okay. Keeping you.
Professor, I have
Yes.
a bit question.
Mhm.
How can we choose which one is in front, which function is in front, like precisely?
From the picture. So you need to figure out uh, from the curve. So, for example, if you remember what we did in the, I think, um, early classes or maybe in basic math, if we have y squared of x, this is actually similar to x equal y squared. So we may draw this first. Okay, we may draw this first, and then if you remember to shift the graph y, and then shift the graph. So x minus 1 means we shift the graphs 1 unit to the right, right?
Yes.
So it's actually the same square root of x, this graph, and then we move unit here, and then this will be the square root of x. Okay? Now, how do we know that this is over here? That's pretty practically from the skills that you have. So some of essential functions, like the quadratic, trigonometric, the exponential 1 over x, the logarithm, you need to at least know how to visualize those essential functions to help graphing um, the the curves. Okay?
No, no, no. Professor, in the integral, how do we know that we have to put like square root of x negative one first? Like,
Yeah, because it's upper, it's on the
oh,
top. Okay.
understand,
Yeah,
understand
yeah.
now.
Okay.
Thank
Yeah.
you, thank you. Yeah.
So this is so. Uh, I think this is also important. So actually, from the area between curves, if you look at from the beginning, it's always that f minus g, right? It's always this the top minus bottom, okay? And in our example also the top minus bottom. Okay, this is the top minus bottom. And when you have the this example here, this is also the top minus bottom. But if you rotate, okay, the top is here, top and bottom here.
Oh, got it, Professor. Got
Okay.
it. Thank you. Thank
So
you. Got
so
it.
so for dy for dx it's always top minus bottom. So for the example here it's also the same. So we can take the x minus 1 as 1 over 2. We integrate. So this will be 3 over 2 and then 2 over 3 over there. And then minus this is x squared over 2 plus x. And then we are going to have from 1 and 2, we will get the, if we put 2, this will be 2 over 3. 4 over 2 minus 2 plus 2 will be 0. And then minus 1, uh, 0. So it should be minus half. Should be 1 over 6. Okay, now if you want to take another approach, okay, we can make this, check. We can make this y squared is, or plus 1 is equal x. And we can take this x, y plus 1. Now, we will have, so we need to check the points. So when x is 2, then y is 1. When x is 1, y is 0. Okay. Now we can actually write this in terms of dy. You can write dy from 0 to 1, right? 0 to 1. And then for now it's y plus 1 minus y squared plus 1. And then dy. Okay, is it correct? So this will be, turns out, from 0 to 1, so half minus 1 over 3, which is also, I think this is better, right? Better approach. So I think this is better calculations. I think you can prevent your mistake by removing the square root in your integrations, so you can make this much more simple. Okay. Now the second one. Anyone got the answer for the second one? Kim, half. Yeah, correct, half. Yeah. So first, we drawing the curve. Then we can start by the x cube should be, or maybe we start with x. We can draw like that. This is y equal x, and then we have cubic. Uh, okay, maybe about that. Okay, so we can define our point. We define point here and here. This is the y equal x cubed. So we can define the intersections as x cubed minus x equals 0, x squared minus 1. And we can factorize. So we know that this will be 0, and then x equal negative 1, x equal 1. So this is 1, and this is negative 1, right? Okay, now, because we know that the cubic has some symmetry, right? So if we take this as A1 and A2, we know for sure, because of the property of the curve itself, A1 is equal to A2. So we are just looking at a half of it and then multiply by 2. I think it's way much easier. So let's look on 0 to 1. So let's look on 0 to 1. So area, we can have multiply, so twice of 0 to 1 of x minus x cubed, and then the x. So y we have 2. This is by symmetry. And then we can take this x squared. And then 0, 1, 2. So it's half. I don't think if you change to dy, it will help because it will be a cubic root, right? It will be a cubic root, and I believe that will be way much having easily to have mistake, right? I think I will let you try the last one. I will give you the graphs. Okay, the graphs. If you take this, if you take the graphs, if you start by taking the cosine, if you take the cosine, maybe this is 1. It's going down and then going up. This is y equal cos x. Now if you have 2 minus cosine, so it start from here, start from the beginning here. Let me write in a different color. It will be goes through here. That's not really good. Maybe let me help line here. Okay, that will be 2 minus cos x. And basically you can let this 2 minus cos x from 0 to 2 pi. And I think it's not that difficult. Okay, if we have time, we will have more review. Maybe next week we will have more review. Yeah, 4 pi. Correct, 4 pi. Okay, I will leave this for you to try. Okay, good. Okay. Okay. Anyone haven't scanned the QR code? Let me stop the sharing here and let me give you the QR code first, and we can continue the. Okay, let's continue. Okay, let's continue. We may have. So chapter 6 mainly speaks about the area between curves. Area between curves and volume. Okay, now we will move to the second part of chapter 6. This will be about the volume. So volume, we are start with we look on this. Okay. If we take this as our so we have a solid. Okay, we have a solid above the x-axis, and we have a cross sections, which is the area, the AX cross section area, and we have point A and point B. So it's in between point A and point B. So the solid is a random shape. Okay, it's a random shape. So we cut the solid and it has this area. And if we divide this solid, okay, if we divide, so make another slice. So we slice. Okay. And if we take this into into several slices with several width. Okay, we take these slices and take the delta and with the width, okay. And we have, for example, as an illustration, we have seven. Okay, we have 7 slices, and we take the x0a and x7 as b. Now, if we remember the sum of the formulation in the volume, we may we may see some of the figures that easily to imagine. For example, the cylinders or any three-dimensional shape that you can imagine. So the idea behind the volume is always it's always base multiplied with height, right? For the volume. So if you have a cylinder, your base is a circle, so you have pi r squared, and then you have h for height, right? Now, if you look here, if we imagine that this slice, if the cross section has an area, then the area multiplied with the delta x as its height, we can make the approach for the volume for some s is approximating equal to a for some x, okay, multiply with the height. And if we have more, then we have summation from the first slice into some n. If you have more slices, a xi and then double x. Now, as usual, as n getting larger, so as n getting larger or getting infinity, then we are going to have our approach or our approximation similar to the Riemann sum that we have before. Then let me write the definitions in more official. So let the S be a solid that lies between x equal a and x equal b if cross-sectional area of S in the plane, let's say plane px, okay, because it's on the some plane there, through x and perpendicular to x-axis is ax. So ax will be the cross section that we talked before, where a is continuous function. Then volume of S is v is the limit as n larger, summation from I equal 1 to n ax delta x, and then it's equal with the Riemann sum definitions, integral from a to b ax dx. So that's the first definitions in volume. Okay. So another thing that I think quite essential, and perhaps it will be obvious if you look through, that uh, although the solid is above the x, and you can see that it's kind of three dimensions, but it's not in the three dimension yet in our discussion later. But this is, we are going to look on just two dimensions, x, y. So what will be, the easiest way to imagine this? So this can be imagined as, if you have curve, for example, the curve that is precisely like this. If you imagine the curve and then rotate the curve, rotate here, the curve, maybe the curve is completely like that, and then you will have something like, so if you have something like this, you rotate, then you have a solid, right? You have a solid, like a circular solid, okay? And that will be our things in the volume, okay? Okay, now if we take approach to, let me imagine this, and wait, not this, maybe this better. Let me crop this first, explain to you. Okay, now let's imagine a sphere. Okay, a sphere, a sphere with the radius r. So it's not a circle, it's a sphere. It's like a ball. And then we slice the ball. Okay, we slice the ball. We slice, and it's become this red color here, slices. Okay, and the slice is a circle, right? The slice is a circle. The circle with the radius y. Okay? Okay, now if we imagine this, if we imagine the cross section, so imagine this as our cross section area. And we define the cross section in x variable. So we define this as a function of x. So first we define this as pi. Let's write y squared, but we need to exchange y into x. Okay, how we can do that? We can have this triangle here. We can have this triangle, which is r, y, okay, and then x. So from here we can say that y squared plus x squared is r squared. Of course, this is the circle, right? The circle equation. And then y is square root of r squared minus x squared. Okay. Now we can exchange this and write down into our y squared. So pi is r squared minus x squared. Right. Now this is our area, the cross section. Now if you want to find the volume of this sphere, then we can find through the volume integrations. Okay. Let's make our radius. If we have this radius, and from here to here, or if we make it, so we are making more to the x, sorry, to the x, so this will be slicing. So this will be the negative r and r. So if we calculate and if we imagine that this is another slicing, then we can say that the volume from negative r to r is equal to ax and dx. This is the height, right? The height of dx here. So ax is r squared minus x squared and then dx. So we integrate with respect to x. So x r squared minus x cubed over 3 from negative r to r. Now we solve this and we find that this will be r cubed minus r cubed over 3. Oh, sorry. Forget pi. We need to write pi there. So I need to write pi. Forget to write pi. Pi. Okay. So this and then minus r. So minus r squared. So minus r cubed minus plus r cubed, right, over 3. Or I think we can take the symmetry. We can take the symmetry to make it much more easier to count. So let's take the symmetry. Take the symmetry. Two pi 0 2 pi. Yeah, I think it's much more easy to be compute. So 2 pi r cubed minus r cubed over 3. Or this will be equal to 2 over 3, 4 over 3 pi r cubed, in which this is the volume of the sphere, right? So through the integrations, through the volume of so finding the volume of the solids through integration, we can actually find and derive the volume of sphere, which is pi over 3 pi r cubed, right? Okay. So maybe any questions first? I think I will just stop until here. Okay, I will just stop until here, and we may have another uh, another sections on next Tuesday with more examples. Do you have any questions so far? Okay. As far as I know, for I think I mentioned in the early class today, right, that we might have for quizzes, probably online quizzes, but for final exam, the default should be offline. Some of you are asking whenever they can have an online exam. Well, it actually depends. Okay? If you are unable to attend, then perhaps I will prepare the online exam. But of course, the percentage for online will be different, and how your score will be counted also different. Okay, so the default should be a physical exam. Actually, after some confirmations through the school, they said that these 2 weeks should be online, but after that, actually we can have a physical class. But I think for me, to make sure that we are safe, then the physical will be just for exam. I think, just for the final exam. So the other, like the lecture, we are just having our online lectures, and the quizzes will be online. Okay. So that's the, I think, information that I've just heard and already confirmed. So yeah, I think for the next week, we will have online lectures like this, and hopefully it will it doesn't, although the interactions and the engagement is not the same as we have in class, the physical class, but I hope we still can have a good learning experience. Okay? And I'm trying my best to provide all the necessary things for students to learn. Okay? And if you now still in isolation, self isolation, I hope you get can have better health in the future, and I hope you stay safe. Okay. So I think that's all for today. If there's no question, any questions? I will just stop here. Okay. I think it's enough. Okay. Anything? Okay. Okay. If not, then please make sure you check the Moodle system. Okay. At least maybe this weekend. Okay, this weekend I will prepare some um, online materials or quizzes or maybe additional videos for you. Okay. So see you again next Tuesday.